Imagine your protection relay's data feed just stops right in the middle of a fault. In this explainer, we're diving into exactly how modern digital substations guarantee that protection-critical data never gets lost. We're looking at network redundancy today for high-stakes environments like generator transformer blocks. When a fault hits, detection absolutely must happen in milliseconds. So the network carrying those trip signals, it has to be totally bulletproof.
Think about this real-world scenario. An Ethernet cable gets pinched during construction work, or a switch just loses power at the absolute worst possible moment. In a digital substation, your protection scheme is really only as reliable as its communication network. If the network drops a signal, well, it's functionally the exact same thing as a relay losing its physical copper wiring. It's a catastrophic failure mode. But today's redundancy protocols are built specifically to make this exact scenario impossible.
Here is our roadmap for the explainer today. 1. The dropped signal threat. 2. Zero switchover time explained. 3. PRP dual independent networks. 4. HSR, the seamless ring. 5. Comparing PRP and HSR. And 6. The explainer summary.
Section 1. The dropped signal threat.
So why is a dropped signal such a big deal? Well, what people often miss here is they assume the phrase redundant network automatically means instant failover. But older legacy schemes, like the rapid spanning tree protocol, actually have a measurable reconvergence time. After a failure, it can take 50 milliseconds to multiple seconds to reroute traffic, and that is dangerously slow. Time-critical goose trip messages need to arrive in single-digit milliseconds to prevent catastrophic equipment damage. In this context, 50 milliseconds is literally an eternity.
Section 2. Zero switchover time explained.
So, how do modern protocols fix that dangerous delay? The fascinating part is that both the Parallel Redundancy Protocol, or PRP, and High Availability Seamless Redundancy, HSR, are designed for an effectively zero-time failover. They don't just minimize that dangerous time gap, they erase it completely.
This brings us to the IEC 62439 standard, which actually defines these two complementary protocols. Both of them completely bypass that traditional detect and reroute delay. Why? Because the redundant path is already carrying the exact same data in parallel. There's zero switchover time because there's nothing to switch over to. Let's look at exactly how each of these ingenious methods actually works.
Section 3. PRP, dual independent networks.
Let's break down the first of these, PRP. What's really interesting about its physical architecture is how each node, like your protection relays, is attached to two completely separated independent networks. We usually call them Network A and Network B. They operate entirely in parallel and can even have totally different physical topologies. The sender just transmits two identical frames over these separate networks at the exact same time.
Now, if network diagrams feel a bit abstract, think of it like this. PRP is like mailing two identical copies of a super important letter via two completely different couriers. If one courier's van gets a flat tire, the other copy still arrives perfectly on time. When the receiving node gets that second duplicate letter a fraction of a millisecond later, it just silently discards it.
Let's pause for a second here. We've talked about a pinched cable, but before I tell you the answer, what do you think happens if an entire network, let's say all of network A, its cables, its switches, the whole shebang, fails all at once?
The answer is absolutely nothing changes. The system keeps working seamlessly because full, identical duplicate frames are continuously sent over two entirely separate networks. Losing one complete network just means the receiver stops seeing duplicates. There is zero interruption to the actual protection logic or the continuous checking of the substation. It really is an incredibly robust solution.
Section 4. HSR, the seamless ring.
But what if you don't have the physical space or the budget to build two entirely separate networks? Well, that brilliantly illustrates the need for HSR. If PRP is two couriers, HSR is like sending a message both clockwise and counterclockwise around a circular relay race. If a runner trips and there's a break on the track, it doesn't matter. The runner heading in the opposite direction still arrives safely.
From a technical standpoint, HSR applies the parallel operation principles of PRP, but onto a single ring topology. The sender node sends two frames, one out of each of its two ports. These frames circulate in opposite directions over the ring. Every intermediate node just forwards the frames it receives onto the next node. Crucially, when the originating node receives the very frame it originally sent out, it discards it to avoid creating an endless data loop. Oh, and a quick operational note based on the ABB specs. An HSR ring supports up to 30 relays. If you have more than that, you're going to want to split the network into several rings to guarantee that real-time performance.
Section 5. Comparing PRP and HSI.
So, how do you actually choose between these two powerful options? When you weigh these features against each other, both give you that absolutely critical 0-millisecond failover time. But as a rule of thumb, PRP really suits layouts that already have two fully parallel physical networks. HSR, on the other hand, is much more practical for compact switchgear rings, which definitely reduces your wiring and your overall physical footprint. We do have to remember real-world engineering pragmatism here, though. These protocols are incredible, but they aren't magic bullets. They protect against a single point of failure. If an excavator cuts through both sides of your HSR ring at the exact same time, you still have an outage. Redundancy protocols absolutely do not replace the physical protection of your cables or rigorous cybersecurity hygiene.
Section 6. Explainer Summary.
All right, let's wrap up everything we've uncovered today. You now know how to recommend PRP versus HSR based on physical layout constraints. But most importantly, you know why their zero switchover time completely outclasses older spanning tree methods. When a fault occurs, your system will not waste precious milliseconds trying to find a new path. It acts instantly.
We've guaranteed the signal won't be lost in transit, but a perfect, instantly delivered signal is really only as good as the logic waiting to act on it. So, with reliable data now securely flowing, how do we structure the actual protection logic for the plant's highest value asset, the generator transformer block? I mean, if this bulletproof network delivers a perfect signal, but the relay logic makes the wrong call, what happens then? Think about that until next time.